Okay, since the lecture capture didn't work for lecture 16, what I'm going to do in this video is to go through the lecture slides and pick out the major points. I'm not going to try to reproduce the whole lecture, as I say, just picking out the major important points from what we covered. We began this lecture with the review of the role of the Gauss-Markov assumptions in proving that ordinary least squares is the best linear unbiased estimator. We can list the Gauss-Markov assumptions as follows. The expected value of the error terms is equal to 0 for all values of I. Secondly, the expectation of the product of two different error terms, ui multiplied by uj, is equal to 0. In other words, the errors are independent of each other. Thirdly, the expectation of the squared error, ui squared, is a constant, sigma squared u, for all values of I. In other words, the errors exhibit what we call homoscedasticity, or constant variance. And fourthly, the x's are not themselves random variables. So when we take the covariance of xi and ui, the expected value of xi multiplied by ui, we can take the x outside that expectations operator and write that as xi multiplied by the expectation of ui, which is of course 0. And the question we're going to ask today is what happens if the x's are themselves random variables. If the x variables are stochastic, then it's very difficult, if not impossible, to form expectations of the OLS estimator. We've already derived this expression here, the expected value for the expected value of beta hat. And the problem we have is that when we try to take the expectation of this ratio of numbers, then the expectation of the ratio of two random numbers is not equal to the ratio of their expectations. And similarly, when we want to take the expectation of the product of random variables, for example the expected value of the sum of xu, where both x and u are random, then that's not equal to the product of their expectations. Given this, we need to look at another property of estimators, which is consistency. And consistency is a rather weaker property than unbiasedness, as we'll see in a moment. Well, first of all, let's consider what's meant by consistency. For an estimator to be consistent, its probability limit must equal its true value, beta. So the plim of beta hat must equal beta. Well, what do we mean by a probability limit? Well, probability limit is essentially what happens to the probable value of the estimator as the sample size becomes large. So we would say that the probability limit of beta hat equals beta if the limit of the probability that the difference between beta hat and beta is greater than some number epsilon goes to 0 as the number of observations becomes large. So as the sample size gets bigger and bigger, the probability that our estimator is close to the true value gets larger and larger. Note the notation here. When we write beta hat n, what we mean is the estimator of beta hat based on a sample of size n. So if the plim of beta hat equals beta, we say that the estimator is consistent, and if the plim of beta hat is not equal to beta, then we say that the estimator is inconsistent. And sufficient but not necessary conditions for an estimator to be consistent are, first of all, that the limit of its expectation should equal the true value as the sample size gets large, and secondly, the limit of the variance of the estimator should be equal to 0 as the sample size gets large. And I need to stress these are sufficient but not necessary conditions. To illustrate these, let's consider a probability density function for an estimator which is biased in small samples but nevertheless is consistent. So here I've drawn a succession of probability density functions for larger and larger samples. The true value of the parameter here is 0.5. Now what we see is that in small samples, for example given the PDF given by the red line here, the probability density function is not centred on the true value, it's away from 0.5, and the variance is quite large. It's got a big spread. As the sample size gets a bit larger, then the probability density function is given by this blue line here, and we can see that the peak of the distribution has moved closer towards the true value, 0.5, and the variance has got smaller. The sample size gets larger still, then the peak moves towards the true value of 0.5 and the variance gets even smaller. Now, in the limit, if the PDF is centred on the true value of 0.5 and the variance becomes 0, so effectively the PDF becomes a vertical line passing through this particular point, then we would say that the estimator is consistent. Now, consistency is typically a much weaker property than unbiasedness, and estimators that are biased in small samples can still be consistent. And there's an example of that here in this handwritten example, where we've got a sequence of random variables xi, each of which has got mean, mu and variance sigma squared, which are unknown. Now, suppose we want to estimate mu. We could take as an estimator the following expression: 1 over n minus k, where k is some positive integer, multiplied by the sum of from I equals 1 to n of xi. Now, this is not a particularly sensible estimator to take, but nevertheless we can show that it's consistent. It's a biased estimator because if we take expectations of x here, x hat, then that would be equal to n over n minus k mu, which will obviously be greater than mu. However, it is consistent estimator because the limit of that expectation as n goes to infinity is equal to the true value mu. That's fairly straightforward to show. And also its variance, which is given by this expression here, n over n minus k squared multiplied by sigma squared, is equal to 0, because if we take this function of n here and look at what happens as n goes to infinity, then we can show that this function goes to 0. So therefore, this estimator, which is biased in small samples, nevertheless satisfies the sufficient condition to be consistent. Now, the big advantage of probability limits is that they obey certain rules which do not hold for the expectations operator. So we can do things with probability limits that we can't do with expectations. For example, let x and y be random variables. We can show that the probability limit of x and y is x multiplied by y is equal to the product of the probability limits. So plim xy equals plim x multiplied by plim y. Not true for expectations. Similarly, the probability limit of the ratio of the two random variables is equal to the ratio of their probability limits, provided the random variable on the denominator does not have probability limit 0. So plim x over y is equal to plim x divided by plim y, provided that plim y is not equal to 0. Finally, if we take a function of a random variable x and we take the probability limit of a function of a random variable, then that's equal to the function of the probability limit of x. Plim g of x equals g plim of x. None of these rules applies to the expectations operator, so we cannot do these things with expectations, but we can do them with probability limits, which means that we can evaluate probability limits in circumstances where we can't evaluate expectations. And using these rules, it's often possible to show that an estimator is consistent, even if we can't show that it's unbiased. Now let's turn to the OLS estimator. If we take the OLS estimator with stochastic regressors, then we can write the following. We've got our expression here for beta hat as the sum of x, y divided by the sum of x squared. Substituting for y gives us this expression here. And then by a little bit of algebra and some manipulation, we can write this as beta plus 1 over n times the sum of xu divided by 1 over n multiplied by the sum of x squared. Now, I've divided numerator and denominator here by n because what I want to do is look at the properties of this estimator as the sample size becomes large, in other words as n tends to infinity. Now we're going to assume that a couple of conditions hold here. First of all, we're going to assume that the probability limit of 1 over n multiplied by the sum of xu is a constant, a finite constant. And that's going to be the covariance of the x variable with the error term u. And we write that here, sigma xu. Secondly, we're going to assume that the probability limit of 1 over n multiplied by the sum of the x squareds is also a finite constant, and that's the variance of x, which we write here, sigma squared x. Now, I have to stress, these are assumptions. They may not be satisfied in practice, but nevertheless they're reasonable, form a reasonable starting point for analysing whether or not OLS is going to be consistent or not. So what we've assumed is we can write the plim of 1 over n multiplied by the sum of xu as the population covariance of x and u, and the plim of 1 over n multiplied by the sum of x squared gives us the population variance of x. Okay, now using that we can write the plim of beta hat is equal to beta plus the ratio of the covariance of x and u to the variance of x, or beta plus sigma xu divided by sigma squared x. Now, provided x has got some variation, sigma squared x is not going to be 0. So providing x is not a constant, there's going to be some positive variance here. And therefore, the condition for the OLS estimator to be consistent comes down to the assumption of whether or not the covariance of x and u is 0. If the covariance of x and u is non-zero, then we have an inconsistent estimator. But if the covariance of x and u is equal to 0, then we have a consistent estimator. So this is a rather weaker condition than the previous Gauss-Markov assumption 4. We're no longer assuming that the x's are non-random variables. Instead, we're assuming that x is a random variable, but it's a random variable that's uncorrelated with the error term. And if that's the case, sigma xu will be 0, and beta hat, the OLS estimator, will be a consistent estimator. But if sigma xu is not equal to 0, there's a non-zero correlation between the x variable and the u variable, then the OLS estimator will be inconsistent. Essentially, this is a sort of rather weaker assumption about the exogeneity of the x variable. Instead of the x variable being fixed in repeated samples, we allow x to be a random variable, but we assume that it's uncorrelated with u in order to get a consistent estimator. Now we can show again that an estimator can be biased in small samples but still be consistent for large samples. So let's take an example here. Suppose we use as our estimator, instead of the OLS estimator, we use beta hat n with sample size n as the sum of xy over the sum of x squared plus 1 over n. Again, not a particularly sensible estimator to use, but what we're doing is we're using this to make a point. We're making the point that we can have an estimator which is biased in small samples but consistent in large samples. It's clearly biased because if we take expectations of this, then the expectation of this estimator will be beta plus 1 over n. But of course, because the probability limit of 1 over n is equal to 0, then this estimator will still be consistent. So we can have estimators which are biased in small samples but consistent when we take a large sample. Just to finish up, a couple of things here. First of all, why might there be a correlation between the x variable and the error term? So under what circumstances might we get an inconsistent estimator? Well, we can show that this occurs in two important cases. First of all, if the x variable is measured with error, what we call the errors in variables model. Notice it doesn't matter whether or not the y variable is measured with error, because that's taken account of by the fact that we've got an error term u in our equation. But if the x variable is measured with error, we'll get an inconsistent estimator. The covariance of x and u will be non-zero, and the plim of beta will not be equal to beta. That's something we're going to cover in the next lecture. Secondly, suppose the equation we want to estimate happens to be one equation taken from a set of simultaneous equations. Again, this gives rise to circumstances in which the covariance of the right-hand side variable x and u is non-zero, and we get an inconsistent estimator. Plym of beta hat is not equal to beta. This is referred to as the simultaneous equations model, and again this is something we'll cover in detail later on in the course. Now, you might be tempted to think, given that the covariance of x and u is a key factor here in determining whether or not an estimator is consistent or not, it might be tempting to try to test this condition by looking at the relationship between the x variable and the regression residuals. So we use the regression residuals as an estimator of the errors, which are unobservable, and we look for whether or not there's a correlation or non-zero covariance between the x variables and the u hats and the regression residuals. But we've got a problem. The problem is that by construction of the OLS estimator, the x variables and the regression residuals are uncorrelated. So we cannot use this as the basis of a test for the non-zero or zero covariance between x and u. We can show that as follows. The definition of the regression residuals is y minus beta hat x, and substituting for beta hat we can write that as y minus x multiplied by the sum of xy over the sum of x squared. Now, multiply each of the u hats by the associated x, xi, and take the sum of those. So we get the sum of xi ui hat equals the sum of xi yi minus the sum of xi squared multiplied by the sum of xi yi divided by the sum of xi squared. Now, cancelling the sum of xi squareds in this second expression here just gives us the sum of xi yi minus the sum of xi yi, and of course that's equal to 0. So if we're going to test for a non-zero covariance between x and u, we've got to find another way of doing it. There are potential methods for doing this, but again, this is something we'll need to leave for a later lecture.